Hello, everyone. Today I'm going to talk about the um, answering private linear queries adaptively using the common mechanism. Okay, so suppose we have a private data set and we would like to get some information from this data set. Then we need some private queries to get information from the data set. Suppose now we have this first mechanism. So suppose the original data set is a demographic data. And now we are trying to get noisy age by race marginal. This is the first type of mechanism that we want to get from the dataset. At the same time, we're not sure if this is good enough. So we also have the other set of mechanism, which basically are two one-way marginal. The first marginal asks for the age marginal, and the second one asks for the noisy race marginal. So the analyst is curious about which mechanism is better. He doesn't know which one is better because he always need more information because you can know the answer before you actually look at the data. So the price solution basically spend part of the privacy budget to look at the data and get partial information from the data sets. And based on the information he gets, he will decide to choose which mechanism would be better. So suppose that in the demographic data, he found out that there's a larger population, that it might be better to get the noise age by race marginal. However, if the population is small, the answer to the age by race marginal would be very sparse. It means that the noise will swarm the data. And as a result, the answer will not be that useful. So it might be better to have a more coarse statistics like the one-way marginal, which will have larger signals. And once the analyst decides which mechanism to use, he would then spend the remaining privacy budget to release the private statistics. So this is the prior work, and it turns out that the first privacy part of the privacy budget is only used for selection, and we ask the question whether it can be used to improve the utility for the mechanism that we are interested in. And also, it's a common question that we don't really know how much privacy budget should be used for the selection part, and it always needs some prior knowledge, and it's not very easy to get this how much privacy budget to spend for selection. And sometimes two mechanisms, they share some common information, and the prior works ignore this common information. And we ask the question whether we can find this type of common information and whether we can use this common information to select mechanism. And if we can do this, we can potentially save some privacy budget and also improve some accuracy for the mechanism we choose. So in general, solution looks like this. First, we have the suppose we have this mechanism one, and we try to decompose it into two parts. The first part is M star, and also for mechanism two, we try to decompose it into two parts, and we would find that M1 and M2 they are possibly share the same part of the information. These two types of query can share some common information, which we call the common mechanism. Because these two mechanism they share some common information, it is very intuitive to first answer this common mechanism because this common mechanism can be used later. So we first answer the common mechanism and gets part of the information from the data sets. And based on the answer to the common mechanism, we decide whether we want to use mechanism 1 or mechanism 2. So suppose we are interested in mechanism 1, and then we make use of the remaining part of the mechanism, which is called the residual mechanism. So we already have the answer to M star. Then we will spend the remaining part of the privacy budget to answer M1 prime. And we can combine M star and M1 prime. And they are equivalent to answering the mechanism M1. So in this case, we don't waste the privacy budget for selection because M star can be reused to reconstruct the original mechanism M1. And similarly, if we decide to answer mechanism 2, we can get the M star first and combine with the mechanism 2 prime, we can reconstruct mechanisms 2. In this way, we basically use the first part of privacy budget to answer common mechanism. Because the common mechanism is shared by both two mechanisms, it can be used later for reconstructing the original mechanism. And in this way, the privacy budget spent on the common mechanism is not wasted. It can be reused later to reconstruct the original mechanism so that the privacy budget is saved and the mechanism is as accurate as the original mechanism. So that's the general idea. And then we need to dive into details. So first of all, our framework satisfies differential privacy. And differential privacy is a strategy that protects individual data by preserving the original output so that the output of an algorithm doesn't change much by removing or adding a single user's data. And our algorithm works for linear Gaussian mechanism. So for example, if we have a data set in the that discussed about that calculates the total number of people who is not Hispanic and not adults. So X0 represents the number of people in this data set that is neither adult nor Hispanic. And then X represents a data vector, which is so each entry of the data vector represents the total count of this of certain people that satisfy certain properties. And then we have a matrix representation to calculate the statistics of the data sets. So in this example, the workload matrix B times data vector X represent the query result. So the first query actually calculates the number of adults. So it's X1 plus X3. And it represents the number of adults in the data set. The second one computes the Hispanic individual. So it's X2 plus X3. And also we have the total number of people in the data set, which is just the total sum of the people. And the linear Gaussian mechanism actually add correlated Gaussian noise to the original answer to the data set. And we have the theorem to show that this is differential privacy under certain constraints. So we have a lemma here. So for the linear Gaussian mechanism, if it satisfies epsilon delta differential privacy, the privacy coarse matrix defined as B transpose times sigma inverse times B. So the maximum diagonal of this matrix should satisfy this condition. Once it satisfies this condition, it can be guaranteed that it satisfies epsilon delta differential privacy. And also, this linear Gaussian mechanism works for multiple definition of differential privacy. Specifically, it satisfies zero-centered differential privacy, and also it satisfies mu Gaussian differential privacy. So to get the common mechanism, first we need definition of answerability. For an original mechanism, we say that another mechanism is answerable from M1 if there exists some coefficient that we can do the linear transformation from the M1 to M star. Basically, B star is the linear combination of the rows of B1, and sigma star is also the linear transformation by adding some noise. So we have this important theory showing that if M1 is answerable from M2, the privacy cost matrix is smaller than the privacy cost matrix of M2 and the linear order, which means the first matrix the second matrix minus the first matrix is positive semi-definite. Yeah. So this is important because this privacy cost matrix characterize the properties of the linear Gaussian mechanism. So we call M1 and M2 are equivalent if they are answerable from each other. Using the property, we can construct an arbitrary original mechanism to a mechanism that has some nice property. For example, we add independent Gaussian noise to the original mechanism. Yeah, so once they satisfy this constraint, the property that their privacy cost matrix are the same, it can be shown that they are equivalent, they can answerable from each other. And we say that they are equivalent in that sense. And we also say that this is in the standard form because it has a nice property that the covariance for the noise is independent. So once we get the equivalence, we can define the common mechanism. If M star is answerable from both M1 and M2, it's a common mechanism for M1 and M2. Then we can get the Curie matrix for M1 and M2. We'll find the common Curie matrix by finding the intersection of the row space of B1 and B2. Then we find linear transformation coefficient. And then we find the maximum common mechanism by solving the semi-definite program. If only two mechanisms are involved, there is an analytic solution, which is easy to get. Then we define signal to noise ratio. And the property, based on the signal, so C is the true count, sigma is the standard deviation. And based on the signal to noise ratio, we decide whether which mechanism to choose. If this is satisfied, we select mechanism 1. Otherwise, we select mechanism 2. So there are other strategies to select mechanism based on the answer to common mechanism, but this is just one of them. Once we get the selection, we can reconstruct it from the original mechanism by using the property that the privacy cost matrix are the same. So we have this algorithm to reconstruct the original mechanism from the answer to common mechanism and how to get our residual mechanism. So this is a theorem in the paper, and for details, you can check the paper. Yeah, so, and also we have the experiment here. We work on the Hesperus dataset with domain size 128, and then we count for the how accurate it is to choose from the original dataset. We achieve around 90, maybe 95% accuracy, and we actually save a lot of privacy budget. So this is the experiment and showing that the algorithm is working well. Okay, that's all. Thank you very much.